Five. Okay, ladies, gentlemen, listen up, please. Welcome back to the Ritchie Theatre, and today we are going to continue our odyssey into vector calculus. In the previous lectures, we talked about vector fields, we talked about flow lines, and we talked about the basic operations of vector calculus, divergence and curl. Today we're going to move on to another section of vector calculus called line integrals. Now, there's quite a few sections here, and in fact I'm going to spread this section on line integrals across 3 lectures. So the 3 remaining lectures for this week, I plan to talk about different aspects of line integrals. In today's lecture, first of all, we're going to motivate the topic. And secondly, we're going to define a line integral, calculate a line integral, and look at the geometric interpretations and some examples, of course. Okay. Now, you may be thinking, hang on, a couple of lectures ago we talked about path integrals. What's the difference between path integrals and line integrals? Well, I'm glad you asked. Yes, we're going to integrate over curves in 3D space, but essentially we're going to be given a vector field and we're going to integrate that vector field over a curve. Now, I'm slightly abusing the words here, but you'll see what I mean as we go on. Now, there are numerous applications of line integrals in engineering, physics, and applied mathematics, especially when you're given a non-constant force and a particle moves around a non-straight line. Okay, so a path that's not necessarily a straight line segment and the force can be variable. At school, you learned how to calculate the work done in physics, for example. These line integrals are going to generalise to, first of all, non-constant forces and moving along curves, for example, in 3 space. Now, just like we did with path integrals, we're going to use parameterizations here. That is, vector functions whose image trace out a curve of interest. Okay, so we say a vector-valued function c of t parameterizes a curve, curly c, on this interval if the image of our vector function traces out the curve. So to give you an example, here's our old friend, the helix. And it's in small font here, but this particular vector function c parameterizes the helix. Now, if you just wanted, say, part of the helix, you can, of course, restrict the interval. Okay, so this vector function here would parameterize the first or the bottom third of that helix. Okay, so this should be a little bit familiar from path integrals. Okay, but if you've forgotten all that stuff, don't worry. Don't worry too much. A very important question what is the difference between vector line integrals and path integrals, or scalar line integrals? Well, to define a vector line integral, the important concept here is to specify a certain direction along the curve, curly C. Okay, so to go back to the previous example, there's two ways to trace out this bottom third. You can go in this direction, or you can start at this point and go in the reverse direction. With these vector line integrals, direction is going to be very important. It wasn't important for scalar line integrals or path integrals, but it's going to be very, very important for vector integrals. So in other words, direction matters. Direction matters. Okay, a curve, curly C, as I just pointed out, can be traversed in one of two directions. And we say that C is oriented if one of these two directions is specified. Now, I'll say a little bit more about that when we do a particular question. Now, we refer to the specified direction as the forward direction along the curve. Okay, so for example, you might have a unit circle. That's your curve, curly C. The question is, how is it oriented? Do you want it oriented so it's traced out in the anti-clockwise direction or the clockwise direction? Okay, that's important because the orientation will actually change the value of our line integral in the end. All right, so direction matters. So here's a simple example. Here we have an oriented curve or path from this point to this point. The pink vector here, it looks like a tangent vector. And you can see that, roughly speaking, it's pointing in the direction that that follows the path in this way. Okay? So here's, again, a very basic example similar to the circle that I just drew. You can see here the forward direction is the anti-clockwise or counterclockwise direction. And in particular, this type of curve is a closed curve or a closed path because it sort of circles back on itself. Okay, so how do we define this line integral? Question?
In your previous drawings.
Yes. Yes.
I don't understand. Is C the actual curve?
No, C is the parameterization for the curve.
For the blue curve?
Yes.
Okay.
Yes. Good question. So C is the parameterization for the blue curve. All right. Okay, so the big question. How do we define a line integral? And it's actually very simple, and there's a little bit of geometry involved. This notation here is how we denote the line integral of the vector field F over the curve, curly C. Now, notice we've got a dot here, And the S on the ds, the S is boldface. Okay, so when you see this, you know you're talking about the line integral of a vector field over a curve, curly C. The line integral is just the path integral of the dot product of f with the unit tangent vector. Okay, now the unit tangent vector points in the forward direction of the curve. Okay, very important, very important. So what does that mean? Well, roughly speaking, the line integral is just the path integral of the tangential component of f. So this dot product here is just the tangential component of f. Okay. So let's investigate a little further. Here, the blue curve is just the curly C. The blue vector is just the vector representing f at different points along the curve. And the pink vectors are the unit tangent vectors to the curve. Okay? Now, you notice in this picture there's no hats here. I always like to make sure that we know that we're talking about unit vectors, unit tangent vectors. Okay, so at least in this picture, what f dotted with t means, it's the component of f along the unit vector t. Now, of course, that can change as we move along the curve. So this is when we get down to parameterizations, this is actually going to be a function of little t, right? Just a scalar valued function. Okay, so if theta is the angle between the vector field and the unit tangent vector, then remember that f dotted with the unit tangent vector is just the magnitude of f times cos theta, where theta is the angle between the two vectors at any point. Now, you can see that here the angle is less than 90 degrees, so this is going to be positive, right? But when we say length here, length is a bit of a stretch, because if this angle was, say, between 90 and 180, cos theta is negative. So you'd actually have a negative component there. So when we say length, we really mean, we're stretching it a bit, okay? Okay. All right, so how do we evaluate? How do we evaluate these line integrals? We know how they're defined. It's just the path integral of the dot product of f with t hat, big T hat. Well, we use parameterizations, just like we did with path integrals. But there's an important difference, and this is getting back to direction matters. We must use a parameterization C that traces out curly C in the forward direction. Okay, that's important. That's important. Okay, for path integrals, we didn't care about that. Another important piece of information that we're going to assume is that the vector function C is regular in the sense that the derivative is nowhere the zero vector. Why? Well, we're going to divide by the length of C dash at some point. So we don't want to divide by 0. Okay, in this case, C dash is a non-zero tangent vector pointing in the forward direction. So to produce a unit tangent vector, t hat, all we do is take the tangent vector and divide by its length. So that produces our unit tangent vector, big T hat. Okay, so how do we actually find this or compute this line integral? What's the actual computation involved? Again, glad you asked. From here to here, this is just the definition of the line integral. Now, the tangential component of f along C of t is just this dot product. So I'm going to replace what's in brackets here with this. And we know that the ds element is just the magnitude of C dash dt. Okay, so I can now replace t hat C of t with this and cancel these things out. So we end up with this simple, computationally important representation for a line integral. Okay? So, in other words, this is just the integral that you know. It's the dot product of these two things. You'll get a function of t and just integrate it from t equals a to t equals b. That's all it is. So, just to reinforce what I said, to compute this line integral, go to the parameterization type of form, work out these two dot products and integrate. That's all it is. It's actually very, very simple. So, let's do an example. Let's do an example. Now, in your notes, you might have y minus x squared instead of x squared minus y, but I just changed it. All right, this is a nice question. We're given the vector field, and we're given the parameterization for our curve curly C, and it's from this point to this point. Okay? So let me just show you a picture of the region of integration. So our curve starts here, finishes here, and is just swept out by the image. Here I've got R of t. In the question I had C of t. It doesn't really matter what. It's just not that important. Okay. All right, so how do we do this problem? Okay. So the first thing I'm going to do is differentiate my given vector function. Now remember, you just differentiate in a component-wise fashion with respect to t. So you'll produce the following vector function. Okay, the next thing we want to do is evaluate f along our parameterization. Okay, so along our parameterization, x equals t, y equals t squared, z equals t cubed. So we take each of those components and substitute them in to f. Right, so we're going to get, what are we going to get? We're going to get t squared minus t squared. We're going to get t cubed minus t to the fourth. And we're also going to get t minus t to the sixth. Okay, so this will simplify. All right, so that's our vector field F along C of t. So what we do now is take the two things we just computed and dot them together. That'll produce a real valued function of t, a scalar valued function of t, right? So with the dot product of these two vectors here. Okay, so it's just the following dot product. It'll produce some function of t. So what are we going to get? So the 0 times 1, 0. It's going to be 2t to the 4th minus 2t to the 5th plus 3t cubed minus 3t to the 8th. Okay, so it's quite simple now. We've done the computation. All we do is take this function and integrate it on the interval of interest. In this case, we'll integrate from 0 to 1. Okay, so easy integration. Integrate with respect to t. You can just do that in a fairly easy way. And you get 2 and 7/12. So the actual computation of a line integral is not that difficult because you reduce it through a parameterization down to an integral that you already know. Okay? Now, here's a question for you. What would happen if, what do you think anyway, if I reversed the orientation? So I performed the same line integral, but the orientation of my curve, curly C, was reversed. What do you think the answer would be? Negative, right. So it would be, that's excellent, it would be this answer here with a negative sign with it, okay? And this is one of the reasons why direction matters. Okay, if you change the direction, you're going to change your answer.
What about if it was friction, which is resisting in both directions?
Sorry, say again?
Like say F was friction, where the work done will be positive both directions.
No, I don't think that's... Yeah, I don't think... Okay, a vector field can't act in both directions, in more than one direction. You know what I mean? At a point. Okay, I know what you're saying, but I just don't think a vector field is equipped to do what you want to do with it there. Okay? Well, I guess a vector field it could impede. It could impede, say, the movement of a particle over a curve or something like this, right? But I think, I think what you want to do with the friction in both ways, in both directions, it's not quite wide enough for a vector field. It's a good point, though. Okay. So, a little thing on notation. there is lots of different notation for line integrals. It depends what you're comfortable with, okay? You need to be able to recognise all the different kinds of notations, and we'll talk a little bit about that in a minute. Now, in the following slide, these are the components of the given vector field f. So this is a function, and so is this. And I've used R rather than C to denote the parameterization. Okay? Six different ways to write the line integral, or the work integral, which is it is sometimes called. Now, here this is the definition. Again, I always like to put the hat in there, just so I know I'm dealing with the unit tangent vector. This is called the compact differential form. This emphasises that the parameter, t. Here it's all written out in terms of the components m, n, p, and g, h, and k. And this is probably, well, it's claimed here that this is the most common form. So you need to be comfortable with all of those representations. And if you can put one representation into another type of representation, so that's great as well. Okay, so let's do an example. Calculate the following line integral. Now, this is in a differential form because we see differentials dx and dy. In particular, our curve C is parameterized by this vector function here, moving from t equals 0 to t equals 2. So the direction is specified here, the forward direction. Okay, so how do we do it? Well, it's very simple. Well, it's very simple. It's just a matter of substitution. Okay? So what we do here, we know that x equals t squared, y equals t cubed. Sub them in here, and possibly, well, if we need, it's not required here, but we would if it was another problem. Calculate the differentials of x and y and sub them in there. So dx is going to be 2t dt. dy is going to be 3t squared dt. And then we just substitute into our line integral. Okay? We will produce an integrand that just involves a function of t. So I'll call this I. So substitution into I yields the following. So I'm going to be integrating from 0 to 2. I'm going to replace the 2y with 2 times t cubed. I'm going to replace the dx with 2t dt. Minus 3, I'll just leave that alone. dy is going to be replaced with 3t squared dt. Now, I've got 2 dt's floating around there. I'll bring them out to the right-hand side and then simplify. Okay? So it's pretty easy integration from here, nothing difficult. We've reduced the evaluation of a line integral down to a simple integral that we know how to integrate. Okay, I get something like 8/5. Now again, note that my answer is just a number. Okay, it's not a vector, it's just a number. Okay, so that's one kind of integral. Now note, I can rearrange this into the compact differential form if I really want to. Okay, let me show you. I can write it in the following way. Okay. Now, that dx dy is just the following. Okay, so here I've written the line integral in the so-called compact differential form. But I didn't use it. I just did a straight substitution after I calculated all these parts. I mean, it's simple, so I would recommend that. If you can do that, do it. Okay. All right, let's build the intuition. Here's a circle. I think in your notes I put ellipse, but it doesn't look much like an ellipse here. Given vector field, denoted by the pink vectors in the plane, and I'm interested in trying to deduce, if I can, geometrically, the line integral of this vector field over this circle. Now I've claimed here that the total line integral is negative. Why is that? Why is that? Well, we're going to find out in a minute why that is actually true. Okay. It all comes back to the dot product of the vector field and the unit tangent vector. Okay, you can see here I've sliced the circle into a semicircle, right? Now, if you look along this subarc, look at the angle that the vector field makes with the unit tangent vector. The angle is going to be obtuse, right? So, what it means is that the dot product, which is just this, will be negative because for an obtuse angle, cos theta is negative. Right, let's call this C1. Okay, curly C1. Right. Thus, the integrand here is negative, so the line integral must be negative. All it comes down to is the angle between the vector field and the unit tangent vector. It's not rocket science. Okay? So we've talked about this subarc, right? Let's talk about the other half of the circle. Now, if you look carefully on this diagram, the angle between F and the unit tangent along this curve, the angle is acute. So that means that cos of that angle, cos theta, is going to be positive on that region. Right? So let's call this bottom arc C2. And so the line integral, C2. Oh, C1. Okay. Now, the thing is though, if the line integral is positive up there and negative down there, how do I conclude that the line integral is negative over the whole circle? Anyone? Sorry, say again? Yeah, it's got to do with the magnitude of F. That's excellent. Right? You can see here the magnitude of F is greater than the magnitude down here. Right? So, on the previous comparing F on the top half of our curve, so that was, so that's C2 or C1? Okay, see that F on C1 dominates. Oh. Whoop, hang on, let me go back. Okay, all right. Yep, okay, sorry about that. All right, so why am I giving you all this stuff? Well, these are quite easy to work out geometrically sometimes, or get some intuition for what's going on. And it all boils down to the line integral, the vector line integral is nothing more than the integral of the tangential component of F along the curve. That's all it is. That's all it is. Okay, so here's a good one. Have you learned anything yet? From the following diagram, calculate the line integral of F over the circle. Now, in this particular picture, the circle, it's drawn in 3 space, but it just lies in the YZ plane here. So, anyone? 0. But hang on, I haven't specified a direction yet. Is it, if I specify the full direction as being, say, counterclockwise, is it still 0? Yeah, what about the other way? Yes, it is. Good. So, line integral is 0. Doesn't matter which way you go, because the tangential component of F, so if I draw in, say, tangent vector, the component of F along the unit tangent vector is 0. All right. Determine whether the line integral of the following a vector field around the curve, the unit quarter of the circle, clockwise. Determine whether it's positive, negative, or 0. So let me see if I can draw this in. All right. Who thinks it's positive? Who thinks it's negative? Who thinks it's 0? Who doesn't care? All right. Good. Well, it may not be so clear from the picture, but just drawing in part of the arc here, you can see that the angle between the unit tangent vector and F, it's going to be less than 90 degrees, right? Sorry, say again? Oh. Clockwise. Oh. How's that? Okay. All right. So the angle here, so I should put this into my picture, right? It's going to be between 90 and 180 degrees. So what's the value of the line integral going to be? Well, is it positive, negative, or 0? Negative. Hence, the line integral of our vector field over C is negative. Okay, so in that particular example, you weren't given the vector field. You were just given a field plot. And you have to geometrically work out the sign of the line integral. Okay, good question, that one. Okay, so let's get back to another basic example here. Calculate the following line integral. The nice thing here is that the parameterization is given and the direction is specified by moving from t equals 0 to t equals 1. So, quite easy to do. It's very similar to the previous example that I presented. Evaluate the vector field F along C of t, work out the differentials, substitute. Okay, so x equals t, y equals t squared, z equals 1 along our curve. So dx is going to be 1 dt, dy is going to be 2t dt, and dz is going to be 0 dt. So we take those parts, sub them into our line integral, and then it'll break down to a simple simple integral, sorry. So substitution into I yields the following. So we're going to be integrating from 0 to 1. X squared will become t squared. Dx is 1 dt. Xy will become t cubed. Dy is 2t dt. And, well, dz is just going to be 0 on the end. So again, collect the dt's and form a simple integral. Okay, so if you integrate this, you should get 11/15 according to my calculations. So again, nothing difficult about the computation. The computation's standard. Okay, especially when you're given the parameterization. Okay, this is gold. It gets more difficult when you have to produce the parameterization yourself. So for example, when we talked about path integrals, I talked about formulae for producing, say, straight line segments. Now you have to check that the direction is the specified direction from the problem that you're given. Okay, useful properties of the line integral. You would expect that the line integral satisfies the properties of the integral that you know and love. For example, additivity, linearity, reversing the orientation. So the minus c here means the same curve c, but the direction is reversed. Okay, so let me give you an example of what I mean there. This minus c represents the curve c with the opposite orientation. So in that case, the sign of the unit tangent vector will just be switched around. Okay, so you get this relationship here. You can easily do that from first principles. All right, so the pink, so if this is the forward direction for curly C, then the pink is the unit tangent vector. You just rotate it by 180 degrees to get the unit tangent vector in the opposite direction. Okay, so one last example. I'm not going to actually finish this off. You should finish this off in your own time. But this is just to demonstrate how to use additivity. How to use additivity in these line integrals. Okay? If C represents the straight line segments from this point to this point, and then to this point, calculate this line integral. Okay, so we just